A lot of students are expressing dismay over the latest group activity. I would therefore like to walk you through that activity, question by question, so that you can see the types of thought processes you should be going through. What I'm showing you here is the activity on the left, and a blank document on the right where I will go through and enter some calculations or notes. Don't worry about the program that I'm using on the right. It might as well be a sheet of scratch paper. Okay, the first thing we do is read the background information. In particular, we notice this statement here, which says that we're going to be focusing on the minimum dose principle, so it's probably worth going back and making sure we read that aspect a little bit more closely in order to have an idea of what we're going to be focusing on. The idea of the more diluted a remedy is, the higher its potency is. Seems kind of strange at first blush, and that's exactly what we're going to be looking at. All right, into the questions. Question 1 is asking for definitions of the main types of concentration measures. I'm going to assume that you are able to look those up without too much problem, so I am going to paste them in here. Okay, molarity, moles of solute over liters of solution. Molality, moles of solute over kilograms of solution. Mass percent is mass of solute over mass of solution times 100%. Parts per million, mass of solute over mass of solution. Mass of solute over, these should be overs, mass of solution times 1 million. If we're interested in how many molecules of the remedy are left, which of these concentration measures are the best ones? Well, the issue here is that 2 of them have moles of solute in the numerator and 2 of them have mass of solute in the numerator. Going from moles to molecules is one step using Avogadro's number. Going from mass to molecules is 2 steps because you also have to include the molar mass. So molarity and molality are the 2 that make the most sense here. In the limit of extreme dilution, where the solvent is water, is there a meaningful difference between these 2? Well, in the limit of extreme dilution, the amount of solution is nearly identical to the amount of solvent because there's almost no solute. Secondly, the solvent is water, a liter is equal to a kilogram. So, no, for the reasons I just stated. At extreme dilution, amount of solvent is equal to amount of solution. In water, 1 kilogram equals 1 liter. Which concentration measure will you use for the rest of this analysis? Molarity, because of these 2, molarity is the more commonly used. Suppose you have a glucose solution in water at a concentration of 0.35 molar. You now dilute the solution by a factor of 10. So you take 1 ml of the solution and dilute it with pure water until the new volume is 10 milliliters. What's the concentration of the new diluted solution? So when we do dilution problems, our equation is C1 V1 equals C2 V2. Okay. So our C1 is going to be 0.35 molar. Our V1 is going to be 1 milliliter. We are diluting this to 10 milliliters. So we now solve for C2. How do we do that? Well, let's take this whole side. We're going to divide both sides by the 10 milliliters, like so. The 10 milliliters cancel, and we end up with C2 equals 0.035 molar. So we will put that answer right here. Nope. 0.035 molar. Now, when you get an answer in one of these activities, you should stop and think about it. What happened to 0.35 when we diluted by a factor of 10. 0.035. We moved the decimal place one spot to the left. Let's remember that. Suppose you take the solution you created in question 5, the 0.035 molar, and dilute that by a further factor of 10. So you take a milliliter of this solution, dilute it with pure water until the new volume is 10 milliliters. What's the concentration of the new doubly diluted solution? Well, we know what happens when you dilute by a factor of 10 now. You move the decimal point one place to the left. So our answer here we can get directly, 0.0035 molar. Boom, fast, done. Now suppose you take the starting solution from question 5, the 0.35 molar. So we're going to still do this one now. So I'm going to say, I'm going to label this up here as question 5. Now we're going to do a question 7. So now we are going to use the same equation, and our starting solution is going to be the same thing, 0.35 molar, and we are still taking 1 milliliter of it. And we are diluting it with pure water until the new volume is now 100 milliliters. Okay. So let's divide both sides by 100 milliliters. And we find that our answer for C2 is 0.0035 molar. So now we are asked to compare the answers to questions 6 and 7. And we see that they're the same. So diluting twice by a factor of 10 and once by a factor of 100 give us the same concentration. Now, which of the two dilution methods, twice by a factor of 10 or once by a factor of 100, required less water, and why? Well, let's see. In the first case, we took 1 milliliter and diluted it with pure water until it was 10 milliliters. So we added 9. For the second step of that process, we did the same thing. We took 1 milliliter of that intermediate solution and added 9 more milliliters to it. So diluting twice by a factor of 10 required 18 milliliters, 9 in each step. Diluting once by a factor of 100 required 99 milliliters. So diluting successively requires less water. Okay, moving on. Background, homeopathic dilutions. This is the introduction of the C scale and the X scale. The C refers to 100, the X refers to 10. In question 5, you created a 1x dilution, so you diluted by a factor of 10. In question the 5 to 6, you created a 2x dilution because you diluted by a factor of 10. You then took a milliliter of that and diluted that by a factor of 10, so you diluted by a factor of 10 twice. In question 7, you created a 1c dilution because you diluted by 100 once. So, if you have a 10x dilution, what dilution on the C scale would it be equivalent to? So let's see here. When we do a 10x dilution, so I'm going to say here question 10. So a 10x dilution means dilute by a factor of 10 10 times. Now, each time we dilute by a factor of 10, we move the decimal point 1 over. So just to pick an example, let's take the example we had before. And just so we can visualize what's going on, if we do a 1x, we add a 0. 2x, 3x, 4x, 5x, 6x, 7x, 8x, 9x, 10x. Now, when we are doing the C scale, a C dilution dilutes by a factor of 100. We don't know how many times we need to do that yet. So what we are trying to do is dilute by a factor of 100. We're going to start with the same 0.35 molar initial concentration, but diluting by a factor of 100 moves the decimal point 2 places. So we're going to count how many times we do that to get the same dilution we have here. 1, 2, 3, 4, 5. And there we're at the same one. So this is going to be a 5C dilution. How much water would you need to create a 10x dilution if you start with 1 milliliter of the sample at each step? Well, at each step you are taking 1 milliliter and you are diluting it up to 10 milliliters. So you are adding 9 at each step. So 9 times 10 steps, so 9 milliliters times 10 steps equals 90 milliliters for the entire dilution. How much water would you need to create the same solutions? That means using the C method, so that means 5C. If you start with 1 milliliter at each step. So if you start with 1 milliliter and dilute it to 100 milliliters, then you are adding 99 milliliters for each step times 5 steps equals 495 milliliters. Now, how much water would you need to use to create the same concentration of solution in a single step if you start with 1 milliliter? Put this over here. So we are now on question 13. We are wanting to go from 0.35 molar to this concentration in one step, starting with 1 milliliter. Now, the easiest way to do this is probably C1V1 equals C2V2. So let's take a look at that. So this is C1. I'm going to put that in parentheses. And we know we are starting with 1 milliliter of it because that's what the question says. We don't, and we know our C2 is going to be that. Again, let's put that in parentheses. And so, what we want to know now is what is V2. So, we're going to take this, we are going to divide both sides by this quantity so that we solve for V2. And you plug that into the calculator. So this program that I have on the right acts like a calculator, but you can do this just in your normal calculator. So I'm going to take 0.35 divided by this number here, if I can select it correctly. And we get 10 to the 10th. So we are taking 1 milliliter and diluting it to a volume of 10 to the 10th milliliters. So 10 to the 10th is going to be, 1, 3, 4, 6, 9, 10. 10 billion. But we started with 1 milliliter, so that minus 1, so to determine how much we added is that much there, that many milliliters. So 1, 2, 3, 4, I'm going to There we go. How does this volume compare to that of an Olympic swimming pool, which contains approximately 2,500,000 liters of water? For this, we need dimensional analysis. Question 14. So, we are starting with this many milliliters. We are now going to do dimensional analysis. 1,000 milliliters is equal to 1 liter. And notice that the milliliters cancel. We now have, we want one swimming pool is liters. Okay, and so we need to figure out what that is. So again, using your calculator, 9,999,999,999 divided by 1,000 times, nope, I'm going to do times that, and I'm going to put this in thing around it, which just tells this program turn it into a number instead of leaving it as fractions. 4. And so the answer is about 4 Olympic swimming pools. Okay, so why are successive dilutions used for homeopathy rather than direct dilution? Well, direct dilution is this one. Successive dilutions are these two. And so the reason is much less water is needed. Okay. So we are 17 minutes in and we finished the first section. Now, we have a new section of background to read, homeopathic potency. And we have to read through this. This will take a little bit of time. The most common homeopathic dilution for most remedies is 30C. So we're going to start looking at those. And we already now know how to do things like 30Cs. We also are looking at a specific example of arsenic trioxide, and we have a density of arsenic trioxide right here. We are going to use the extreme case of our first milliliter is solid 100% arsenic trioxide. Now, remembering that 1 milliliter is a cubic centimeter, how many moles of arsenic trioxide are in that initial 1 milliliter? Well, this is again dimensional analysis. So question 16, we have 1 milliliter arsenic trioxide. Okay. We now need to convert this into grams, and we so first we need to convert to cubic centimeters and then to grams. So 1 milliliter arsenic trioxide is 1 cubic centimeter arsenic trioxide, and 1 cubic centimeter of arsenic trioxide is equivalent to 3.74 grams arsenic trioxide. Now we need to know the moles. And so you can get this from a periodic table. We can look up, bring over to this screen, table. Let's just, oh, that one doesn't have the masses on it. Let's find one that does. Here we go. All right. Here we go. Arsenic is 74.9. Okay, so we need to have arsenic 74.9 grams per mole, and oxygen is 15. We'll call that 16.0. Oxygen is 16.0. 2 times that plus 3 times that. And we get here 197.8 grams arsenic trioxide for 1 mole arsenic trioxide. Okay, so we can now get rid of this stuff down here, so we don't need it anymore. And now we do the calculation. So we go notice everything cancels how we want, and we get moles. And so we now need 3.74 divided by this, which you plug into your calculator. And so we have an answer of 0.0189 moles of arsenic. So superscripts and subscripts are hard here. So all right. So we have our answer to 16. If we pretend that 1 mil were a solution, what would be its concentration in molarity? All right, so that's question 17. So this is how many moles. Well, I'm just going to call it this. Moles over 1 milliliter is the volume, but molarity is moles per liter. So 1,000 milliliters in 1 liter gives us 18.9 moles per liter, or 18.9 molar. What is the concentration of a 1C dilution of pure arsenic trioxide? Well, this is pure arsenic trioxide. A 1C dilution, we learned up earlier, is moving the decimal point 2 places, so 0.189 molar. Concentration of a 2C dilution of pure arsenic trioxide. Well, we know that a second C moves the decimal point another 2 spaces, 0.00189 molar. What is the concentration of a 10C dilution of arsenic trioxide? Okay, so jumping from 2 to 10, we could sequentially move the decimal point over by 2 each time, or we can try to look for the pattern here. That was question 17. All right, so let's come over here and look at question 20. Original, 1.89 times 10 to the 1 molar. 1C is 1.89 times 10 to the minus 1 molar. 2C is 1.89 times 10 to the minus 3 molar. Hopefully you can see that. Times 10 to the minus 1 times 10 to the minus 3. So our pattern is, this is staying the same, but the exponent is going down by 2 each time. 3C, 1.89 times 10 to the negative 5 molar. So so we should be able to project forward to 10C is 1.89 times 10 to the negative, let's see, here we go, 4 is 7, 9, 11, 13, 15, 17, 19. 10 to the negative 19 molar. 1.89 times 10 to the times 10. Here we go. That's how we do superscript. Negative 19. Turn off superscript. Molar. All right. How many ions of arsenic are present in 1 milliliter of that 10C low potency dilution of pure arsenic trioxide? Okay, this is again just dimensional analysis. So we're doing question 21. So we have 1 milliliter. We have our concentration, which is 1.89 times 10 to the negative 19 moles As2O3 over 1 liter of the solution. Now, in order for milliliters to cancel with liters, we have to say 1 liter is 1,000 milliliters. We're not interested in arsenic trioxide formula units. We are interested in arsenic ions. So for every 1 mole of As2O3, we have 2 moles of As3 plus ions, and we're interested in how many ions there are. And so for every 1 mole of As3 plus ions we have 6.022 times 10 to the 23rd ions As3 plus. So we plug this into our calculator. We notice everything cancels and we get what we want. So I'm going to assume that you can plug these numbers into a calculator. This is now going to be divided by 1,000. It's going to be times 2. It's going to be times 6.022 times 10 to the 23rd. We get the result, and it looks like 228. All right. What's the concentration of a 30C standard potency arsenicum album remedy? So we did 10C here, and we now know the pattern. Okay, so it might be nice to come up with a formula here. We know that for each C, the exponent of the 10 is going down by 2. So we'll label this. This is question 22. So if we try to figure out a formula for this, and if we call it NC, where N is how many C's we do, let's see if we can figure out what it's going to be. It's going to be 1.89 times 10 to the negative something. Well, we know it's going to be something related to 2N because the value changes by 2 each time. But if we do to the negative 2n, then 1c would be 10 to the negative 2, and 2c would be 10 to the negative 4. So we're off by 1, so we need to subtract 1. So check that and see if this works, and you'll see that the 10c would be 2n or 20 minus 1, 19 with a negative, so negative 19. So this formula works. So if we have our n equaling 30, then we are going to have 1.89 times 10 to the negative 60 minus 1, or negative 59. (1.89) times 10, format text, superscript, negative 59, format text, turn off superscript, molar. Okay. Question 23. How many ions of arsenic are present in 1 milliliter of that? We're doing basically this same calculation here, but we have a different concentration we're looking at. So I'm going to take this, copy it down here, and we now have a different concentration here where this is to the negative 59. Everything else is the same. So we plug this into our calculator, times 2, times 6.022 times 10 to the 23rd, calculate it, and we get an answer of 2.3 times 10 to the negative 38 ions. Now, we can't have a fraction of an ion. So this is where we say take the inverse of the concentration, which is here ions per milliliter. Take the inverse of that, and we can find out how much we need, how much volume we need for one ion. So let's take this, question 24. So I'm going to label this and leave that there. So I'm going to call this now 2.3 times 10 to the negative 38, and I'm going to label it with units, ions per milliliter of the sample. Taking the inverse of that, we get, taking the inverse of this, 2.3 times 10 to the negative 38 ions for 1 milliliter. We want the answer to be in liters, so we know that we have 1,000 milliliters for 1 liter. And so we now take 1 divided by this number, the milliliters cancel, and we multiply this by 1 over 1,000, and you just plug it into your calculator, and you find 4.3 times 10 to the 34th, and what are our units? Liters per ion. So for 1 ion, you need 4.3 times 10 to the 34th liters. 0.3 times 10. I need to memorize this. Superscripts control period. To the 34th. Apparently it doesn't work. Okay. Format, text, get out of superscript. Liters. So that's huge. That's huge. So we're going to convert it to cubic kilometers. All right, so question 25. We are starting with this many liters. Well, what is a liter? There are several ways you could do this. The quickest way is to remember that a liter is a cubic decimeter. You can do it that way, but that is a little bit less common than some other conversions. One conversion that I do hope you remember is that 1 milliliter is a cubic centimeter. So in order to use this conversion factor, though, we first need to convert from liters to milliliters. So we have 1 liter is 1,000 milliliters. We now have the liters cancel, milliliters cancel, and we're left in cubic centimeters, but we are now trying to find cubic kilometers. Okay, so we know that there are 100 centimeters in 1 meter, but we need 3 of those because centimeters is cubed. So one way to do that is this. Another way to do it is to do this. I am concerned about that because it's easy to miss the cube. The other is to cube this. So we are going from cubic centimeters to cubic meters, but what you have to do then is cube the number as well. So we now have that conversion. All 3 of those approaches are mathematically equivalent and they're just fine. We're now going to do the same thing, converting from meters as it requests to kilometers. So a single kilometer is 1,000 meters. That would be meters squared. That's meters cubed. So getting to cubic kilometers, we take these numbers. So we take this times 1,000 divided by 1,000,000 and by 1,000,000,000. You plug it into your calculator and you get 4.3 times 10 to the 22. I really wish these things worked. Okay. To the 22 cubic kilometers. Which is still absolutely huge. All right. We're going to now make our squashed cylinder. Making our squashed cylinder, we have the formula volume equals pi r squared d. Well, we have the volume that we want. That's in cubic kilometers. Okay, so I'm going to take this. I'm going to put that in for the... Put this in for the volume. I'm going to write it in a better way. Okay, the 22nd cubic kilometers. Pi we know, and we're given the depth to use, which we're using the diameter of the Earth. So this is going to be 12,742 kilometers. Okay. Take this. We're going to divide both sides by this. Okay. We're going to divide both sides by pi. So I'm going to take the pi out here. I'm going to put a pi down here. All right. That divided by pi, and this program knows what pi is, and 12,742. Calculate that to find 1.07419 times 10 to the 18th, and that's in square kilometers because one of the kilometers canceled. We're now going to take the square root of this. Again, plug it into your calculator, and we find that the radius of the cylinder is 1.04 times 10 to the 9th kilometers. Okay. We now have this that we can go to. I'm going to put it on this side. And we are looking for something that's 1.04 times 10 to the 9th, 1.04 billion kilometers. So that's going to, if we, these are distances for from the sun are in 10 to the 6th. So we're looking for 1,000 1,000 times 10 to the 6th kilometers. So it encompasses Jupiter. It does not encompass Saturn. So the answer here is Jupiter, for this planet from the sun that encompasses it. What are the chances that a dose of a standard dilution homeopathic remedy of our album will have even a single atom of the supposed active ingredient? So given that in order to have one atom of arsenic in this standard dilution sample that we've just worked through requires an amount of water that is just stupidly large. The answer here is effectively 0. Now, remember back when we introduced this idea up here that 30C is sort of a standard dilution. High potency treatments are 200C. Wow. All right, 200C. So, what is the concentration of a 200C high potency Well, we solved this issue here. Okay, I'm going to copy that down so that we can look at it. So this is question 29. So we now have n equals 200. So our concentration is going to be times 10 to the negative 399. So 400 minus 1 is 399. 1.89 times 10 to the negative 399. Molar. Nope. Apparently I hit caps lock. There we go. All right. What volume in cubic light years would be required to have a single arsenic atom in it? Okay, so we've done this calculation before with a different concentration. Remember we did, let's find it here. So we take the concentration, we take its inverse to find liters per ion. Okay, so let's start with this one to find out ions per mil. We'll just copy that down. So this is going there. This is going to be question 30. Our concentration here. This is now 399. Okay, now this is hard to get a calculator to do because that is just a ridiculously big exponent, or a ridiculously small exponent that you're dealing with. What you can do for this is go to Wolfram Alpha, and I mentioned this in class before. So we're going to do this. Oops, I apparently missed the 6.022 times 10 to the 23rd. And even this program, which can handle almost anything, is having issues with this. But if you do this into Wolfram Alpha, let me pull this up. We can find the answer here is 2.3 times 10 to the negative 378. And our units now are ions per... So this is how many ions are in 1 milliliter, right? So we're now taking 1 milliliter divided by this many ions. This is going to be how many milliliters you need to get a single ion. Now, we know that in 1 liter... Oh, no, let's convert to cubic centimeters right now. That's going to be easier. So 1 milliliter. So we're now in cubic centimeters. We now know that 100 centimeters is 1 meter. But if we're going to cube these, then we have that. We now need to go from 1,000 meters to 1 kilometer, but we want to cube these. So right here. Now we use our conversion that we were given here for kilometers to light years. So we have 9.5 times 10 to the 12th kilometers is in 1 light year. We'll call it an LY. Now this one is harder to do in by just adding zeros. You can't just do that. So I'm going to label this one as cubed like this. So looking at our calculation, we have which you would plug into probably Wolfram Alpha. I am hopeful that I don't have to do that here because of the program I'm using, but if you do, but since you don't have this program, just putting it into Wolfram Alpha will get you the answer. And then put this here, and remember to cube that one. Yep, and so this one was actually too big as well for the program I'm using, so we will again go to Wolfram Alpha. And we get 5 times 10 to the 332 cubic light years. Five times 10 to the 332 cubic light years. Oh, no. Cubic light years. Now, final question. How does this volume compare to the size of the observable universe, which has a diameter of 93 billion light years? Well, so this is going to be question 31. So we have, if we have a diameter of 93 billion light years, then, so let's say 93 billion light years. We divide that by 2 to get the radius. The volume of a sphere is 4/3 pi r cubed. So this is the radius. We are going to cube it, multiply by 4/3, and we're going to multiply this by pi. So we do that calculation, and you can again type this one into your calculator, and that one will work. And it's leaving it in units of pi, so I have to do something that your calculator would normally do to convert it to a number. So don't worry about that aspect. And we have an answer of 4.22 times 10 to the 32nd cubic light years. And we're comparing that to this one. So what is this divided by this? And we find that we have 1.2 times 10 to the 300 universes would fit, observable universes fit into the 200C Arsenicum album remedy necessary to have a single arsenic ion in it. Okay, that whole thing took me less than an hour, and I was talking through all of the details of it. The ideas of the calculations are simple. The key thing to notice, however, is when you have some questions that take you through something like, here's what 1C does, here's what 2C does. Now, what does 10C do? That is asking you not to do a complicated calculation for the 10C. That is asking you to look at the prior calculations and see what's the pattern. Is there a quick way to do this? Okay, so that is my talk through here. And this is the kind of things that I want you to be working your way through as a group on each step. Recognize when a calculation that you are doing is the same as another calculation you had done before. So when you did a calculation here, trying to determine how many ions there are in 1 milliliter of a sample of one concentration, you can later do that same calculation with a different concentration. And you can later do that same calculation with a very different concentration. The procedure is identical, you just have a different number that you're plugging in. Yes, these numbers are huge. Yes, most calculators cannot deal with them. In fact, this program, which does math better than any other program that I know, chokes on it sometimes. When that happens, if that ever happens, call up Wolfram Alpha and put in the calculation there, and it will be able to handle it for you. So, I hope this has been helpful, and I hope that this will help guide you in how you approach these questions in the group activities as you go forward. Thank you for bearing with me through this process. I appreciate it. Your future group activities will benefit from this example.